All right, today we are diving into a really fascinating scientific paper that's tackling one of the biggest challenges out there. How do we create clean, sustainable fuel? We're going to look at how scientists are literally designing brand new materials, atom by atom, to try and spark a whole new energy revolution.
I mean, just think about that question for a second. It sounds like something straight out of science fiction, right? But this is the very real problem that scientists are trying to solve. Imagine a world running on the two things we have the most of, sunshine and water.
Okay, so we all know the deal. We have to move away from fossil fuels. And for a lot of scientists, the ultimate dream is hydrogen. It's an incredibly powerful fuel, and when you burn it, the only thing that comes out is water. So, what's the catch? Well, the big problem has always been figuring out how to make all that hydrogen in a way that's clean, efficient, and doesn't cost a fortune. So how do we do it? Well, there's this amazing process that scientists are working on called photocatalytic water splitting, or PWS for short. The idea is actually pretty simple. You take a special material called a photocatalyst, you put it in water, and you shine some light on it. That material then uses the energy from the light to literally tear water molecules apart into hydrogen and oxygen. The real trick, though, is finding the absolute perfect material to get the job done efficiently. So where do you even start to find this perfect material? Well, that's where the real quest begins. It turns out scientists have a very specific set of criteria they're hunting for.
Yeah, it's not just any old material that can do this job. Scientists have this super demanding checklist. First off, it has to be incredibly tough and stable. It needs to be great at soaking up sunlight. It also has to have these just right energy levels, the Goldilocks zone, if you will, to actually start the reaction. And on top of all that, it has to move energy around inside of it with incredible efficiency.
Now, instead of just searching around in nature for something that might work, the scientists behind this paper did something really cool. They decided to build their own catalysts from scratch, basically designing them atom by atom on a computer. This way, they could try to bake in all those perfect properties right from the start. And here they are. Meet our contenders. These are three brand new, two-dimensional materials. You can think of them as these unbelievably thin sheets, just a few atoms thick. They were built, kind of like atomic-level Lego, specifically to check off every single item on that demanding list.
Okay, so before we even get to how well they perform, we have to ask a really important question. Can these new materials handle the heat? Can they survive under extreme stress? That was the very first test. And the results, well, they're just incredible. This simulation right here shows one of the materials, Mg₃N₄, being heated to 2000 Kelvin. To put that into perspective, that is hotter than molten lava. And as you can see, its atomic structure is completely fine. It's perfectly intact. It didn't break down or fall apart at all.
And, it wasn't just the heat test. All three of these new materials passed a whole bunch of tough simulations, proving they are stable in every way that matters. Mechanically, structurally, you name it. This tells us they aren't just some cool idea on a computer. They have the potential to actually be used in the real world. All right, so we know they're tough, they're stable, but how well do they actually do the job? That's the million-dollar question. And this is where things get really, really interesting. Remember that Goldilocks condition we talked about? Well, this is it, in action. See those gray bars? Those represent the energy levels of our materials. And the blue lines? That's the sweet spot, the exact energy needed to split water. And as you can see, our materials' energy bands fit perfectly. They have exactly the right electronic properties for the job. But here's something that's just fascinating. It's how the energy moves around inside these things. See, for this reaction to work, you need your energized electrons and their positive counterparts, called holes, to get away from each other, and fast. If they crash back into each other, poof, the energy's just lost as heat. Now look at this table. It shows that the holes move dramatically faster than the electrons. It's like they're on their own separate superhighway, which keeps them from recombining. And that is absolutely key for efficiency. So we have stable materials, the perfect energy levels, and this amazing ability to keep charges separated. It's time for the final showdown. Just how efficient are they at turning sunlight into hydrogen fuel? Well, one look at this chart tells you there is a very clear winner. And the winner is Mg₃CrN₄, clocking in with a theoretical solar to hydrogen efficiency of 25.33%. Now, to you and me, that might just be a number, but in the world of photocatalysis research, That is a huge number. For context, a lot of other systems really struggle to even break into the double digits. So this suggests this material isn't just a small step forward, it could be a major breakthrough. And hey, don't just take my word for it. The paper itself points out that this efficiency is, and I'm quoting here, higher than many common 2D PWS materials. In other words, this thing is a potential game changer.
So what does all this add up to? We've got this super stable material designed entirely inside a computer that shows this incredible world-class efficiency. What happens next?
Now, it is really important to remember that this is all theoretical work for now. But honestly, that's what makes it so exciting. This research gives us a powerful blueprint, a recipe for a whole new class of materials that could, one day, revolutionize clean energy. The next step is taking this recipe from the computer and into a real lab. And this is really the future of science, isn't it? This seamless journey from a digital design to a real-world solution. Now, we're not quite there yet, of course, but this research offers a seriously exciting glimpse of a future powered by nothing more than sunlight and water. The question really isn't if anymore, it's when.